Welcome to the Bedrock IDE Demo. This demo will provide an introduction to the Bedrock IDE and discuss the features and usage of the Bedrock IDE, starting with a simple program and ending with a fully functional continuous process plant control and simulation demonstration. A file package is available that complements this video. It consists of a copy of this video, the script of the video with prompts, a PowerPoint version of the video with screenshots and speaker notes, the discrete batch continuous project that is demonstrated in the latter part of the demo, and a copy of the project that is created during the demo. Contact your Bedrock solution partner for more information on this file package. Bedrock is thrilled to be partnering with CODESYS on the development of the Bedrock IDE. Similar to Bedrock, CODESYS was designed from the ground up based on 21st century software development tools and techniques. It has its roots in modern software development tools such as Microsoft Developer Studio and Eclipse, used by 20 million programmers throughout the world. For these reasons, CODESYS and the Bedrock IDE are very powerful and quite easy to use. The Bedrock IDE supports all the IEC 61131 industrial control programming languages. We will show you the power of these languages as well as the benefits of having the power to use the right language for the job. Perhaps the single best feature of the Bedrock IDE is its cost. The Bedrock IDE is zero cost to developers. You can download the IDE from the Bedrock website and begin developing your code today. Not only can you begin developing your code, you can also test your code and develop your HMIs today. The Bedrock IDE includes a full-featured controller that runs on your laptop. The simulator can run all of your control and simulation code, as well as make your tags available on its built-in OPC-UA server for you to develop and test your HMI screens. All this without ever touching any actual hardware. You can enter your plant knowing your software will work the first time, and the plant downtime will be kept to an absolute minimum when you deploy your new hardware and software. CODESYS has taken Europe by storm and is beginning to do the same in the US. Industrial control vendors are beginning to realize the difficulty and expense of maintaining their own development tools when there is a standard available that is lower cost and higher performance. This situation is very similar to the 1980s when PC vendors realized it made much more sense to go with Microsoft than for each to have their own operating system, except for Wang and DEC and some others. And how many Wangs and DECs PCs have you purchased lately? CODESYS is already being used by over 300 OEMs on a wide variety of hardware. OEMs include B&R, Beckhoff, Wago, and ABB. Because of its broad usage, 700,000 licenses sold in 2013 alone, the developers have the resources to make a stable and capable piece of software, and third-party vendors have created thousands of applications to run on top of the CODESYS IDE. There's little doubt that CODESYS is poised to become the Microsoft of the industrial control world, and I am confident that many ICS vendors will be adopting the CODESYS in the next decade, just as the PC vendors did in the 1980s. CODESYS, as I mentioned, has taken Europe by storm and has actually become more popular than even Siemens in Germany. This article from a German magazine a few years back shows CODESYS and its CODESYS-based derivatives on par with Siemens. CODESYS' popularity has grown since, and noticed Rockwell is the little 7% here. Alright, now we'll start with the live part of the demo. First we will show the Bedrock IDE here, and we'll begin a new project. This brings up a new project dialog box that allows us to choose which template we want to use. The Bedrock IDE is actually a group of plugins that work very well together, and you can pick and choose which plugins that you want for specific application. The Bedrock IDE comes out of the box with two different categories. One is for projects and the other is for libraries. We're going to start out with a project. It's going to be a simple project, so we'll just use a standard project, and we'll go with that. The next dialog box that comes up allows us to choose which target hardware we want to use and what language we want to use for the top level. The target hardware is very easy to change once we're inside the IDE, and as is the top level language. So we'll just leave the defaults for now. Alright, this brings up the devices dialog box. This is your main navigation screen for the Bedrock IDE. It shows you hierarchically everything that is in your design. The device, the application, and your program and your tasks. So what we're going to do first is just show you how to install and configure the Bedrock hardware. So the first thing we do is we add a device, and this will be one of our backplanes, the 5, 10, or 20 slot backplane. Now, if we were hooked up to hardware, I could come in here now and just do a scan for devices, and it would tell me everything that's in that backplane and fill it in. We're not hooked to hardware, so we'll do some of that manually here. We'll just install a couple of I/O modules, as well as we will also install the Universal Field Bus module. Okay, and then we'll go and show you how to configure each one of these. So this is our Universal I/O module, the 1.5. It has a it supports heart and heart pass-through. The first screen we see here, the first tab we see here is the heart. This is shows us all the heart mappings and variables for the heart. Since this is a highly configurable I/O module, the second screen shows us how to do that configuration. First, we choose if this is an input or an output. Then we choose what type of input or output we want this to be. So it'd be a current, loop, heart master, millivolt, any type of thermocouple, any type of RTD. And our next module, the SIOU, will also have discrete inputs and discrete outputs choices here as well. Then we choose our engineering units that we want to use. We choose the A to D line frequency. This allows us to synchronize our A to D converters with the local line frequency to avoid beat frequencies and increase accuracy. The next allows us to choose our A to D conversion rate. This allows a trade-off between sample rate and bit resolution, with a bit resolution up to 19 bits. Our analog inputs support loop power. They can provide loop power to your two-wire transmitters. So here's where you would set that option. And then failsafe, we can choose hold last state or go to a failsafe. And if we choose go to failsafe, we select our failsafe value. So that's as easy as it is to configure, and each channel is individually configurable. All right, let's do some mapping. Before we do mapping, we have to create a very simple program to map to. So we're just going to make a very simple program. Output equals input. IEC 61131 is a highly typed language. All the variables must be declared with a type before they can be used. This allows the compiler to find errors that would be very difficult to find once your project is deployed. Fortunately, the Bedrock IDE makes this process simple with the auto declare. What this does is it allows you to determine whether you want the variable to be an input or an output, or the scope, give it a name, give it a type. In this case, we're doing analog in and out, so we'll want real numbers. We can assign it an initial value if you want. There's an input assistant for finding data structures and complex variables. There's an array wizard for creating multi-dimensional arrays. And there's an initialization wizard for initializing complex data structures. Also comments, so we can put comments in. And the beauty of these comments is anywhere you use that variable, if you hover over it, that comment will appear. So I'll show you exactly what that was used for. All right, we'll say OK, and notice it comes up here and fills in the declaration. Now the second one, I'm just going to cancel. I'm going to leave this one undeclared, so I can show you that you can still use the old-fashioned global variable method if you must. So the Bedrock IDE, notice this little red squiggly lines. The Bedrock IDE has a precompiler that is continuously running and checking your code in real time. And here it's telling us, well, we've got a problem in our program. And here it's telling us what the problem is. Identifier input is not defined, as we'd expected. I hover over output, and I do get my comment there, just as we'd expect. All right, so let's go do some mapping. I'll go back here. Do some mapping. This is our universal analog input and output, so we first have to decide, are we mapping it to an input or an output? In this case, we're mapping it to the output, and we can go and I could just type that name in if I want, or I can go find it here in Application PLC Prog and output. There we go. Now that variable has been mapped. This IO has been mapped to that variable. This is the full path name. This is the structured programming technique for mapping your IO variables. I can also use the old global method, and this time now we're mapping an input, so I want to do that on the input side. Now this one I'm just going to type input, And now notice the symbol's a little bit different. This one indicates that we mapped it with a full path name. This one indicates that it's mapped through a global. Now if we go back to our program here, notice a little red squiggly line is gone. That red squiggly line is gone. And we are all mapped and everything's ready to roll. And I also want to show you quickly how we map field bus devices. So in this case, we want to add a device to this, our SIO4.E, and we're going to map we can map either a Ethernet IP scanner or a Modbus device. We're just going to do a Ethernet IP. I'll show you Modbus later on. We will map, go ahead and map the Bedrock, and now we map a device. And in this case, these are devices for the EDS files that I have previously read in to the project. That's a very simple process. Just go Tools, Device Repository, and Install, and navigate to it, Install. I've already done these. We just double click on this BALF model and it brings that in. Then all we need to do is double click on that, fill in its IP address, and map its variables. And here the variables are all defined and ready to be mapped in just the same way I showed you, mapping the variables that are directly connected to the Bedrock hardware. And that's as simple as it is to map a field bus device. Okay, next we're going to show you how to program in the Bedrock IDE. We'll show you how you can use each language for its purpose, and how you can make function blocks that call function blocks of other languages that call function blocks of other languages, and how that's useful. First, we're going to turn off the hardware. We do that by going to the properties and just moving from the build, since we'll be using the software from now on, the software simulator. And the next thing we're going to go do is just delete this program that we don't need anymore, because I want to show you how simple it is to create new programs within the Bedrock IDE. So we just come in, add an object, a POU. POU is IEC 61131 language for Program Organization Unit. These are your programs, functions, and function blocks. So we're going to make a function block called counter. We're going to actually make a program called counter, and we're going to do that in structured text. Structured text is a great language for low-level manipulation, bit manipulation, complex math. It can be used for state machines, but extra complex state machines. It can be used for higher-level programming as well, but we'll show you some other alternatives for that shortly. So counter, program, and structured text. So we'll say OK to that. Then we'll create our structured text for the counter. Count equals count plus increment. Okay, now the auto declare will come up and ask us what we want count. This is a program, so I don't have to declare my inputs and outputs, but it's a good practice to do that anyway, and we'll show you why in a moment. So count will be an output. We can accept the default of type integer. I could give it initials value. I could give it a comment if I want. We're going to skip that for now. And increment is an input, and it's a type integer. I'm going to give that an initial value of 1. All right, there we go. There's our program. There's our initial value declaration here. And so we can go ahead, and now there are two ways to simulate this code. First off, the Bedrock IDE has a built-in simulator that works well. The only downside to that is it doesn't have access to the outside world, so you can't use that if you want to read or write files, or if you want to use OPC-UA server, or if you want to connect it to field bus devices. But other than that, it works great. It does have the advantage that it runs forever, doesn't time out. So we will use that for the beginning of our demo here. We do that by just going online and simulate. Before we log in, we do need to put this counter under a task so that it will execute. So this is a program. We need to give it a task, assign it to a task, and we'll show you more of that later on in the demo. Then we can log on. I can select this line here, and I can hit the F9 key to set a breakpoint. I can start off the simulation. It breaks right there at the breakpoint. I can hit F8 to single step, as it watches its single step counting up. I can reset values, so I can take my count value here and I can reset it to 0 if I want. If I type the number 0, right, there we go, 0. I can hit Control F7 to write that, or I could force that. Either way, and then we can continue on single stepping. Or we can just go ahead and remove that breakpoint. Before we do that, let me show you, you can actually have very complex breakpoints here. We can have breakpoints depending on what task you're in. You can have it break on certain conditions. You can have it break if a Boolean is true. If it breaks, you can have it actually execute some other code for some automated testing. So very complicated. and very powerful. We'll hit F9 just to remove the breakpoint, and there we go. And we can, while it's running, we can still change the value as well and do that, reset it to 0 that way. You can add watch lists and all the features that you'd expect. You can step into, step out of, step over, step to the next step, things like that. Everything that you'd expect in a full-featured simulator. All right, so now let's stop that and let's go ahead and show you another language. So the one tenet of good structured programming is to avoid duplicating code. So in the bad old days, we'd just copy counter, make a copy of it, and then so say we needed something with 2 counters in it, or more applicable would be like if you needed 2 pumps or something like that, a 2 pump skid or a 3 pump skid. You'd take your 1 pump and you'd copy it, and you'd add a 2nd pump to it. Now you've got duplicate code, and you've got in 1 pump and 2 pump. So we avoid that. One way to avoid that is by using functions and function blocks. These are also somewhat similar to add-on instructions in the Rockwell, but much more straightforward and much easier to use. So let's make ourselves well, first of all, what we want to do is we want to change this program into a function block so that we can call it from another program. And there's 2 ways to do that. I could just come up here and I could type function block, or I can flip over to this tabular view here. Some people prefer the tabular view, some people prefer the textual view. But once in the tabular view, we can just double click on this and just say function block. And we say OK, and now it becomes a function block. Go back to the text view, see it says function block. Over here it's changed to an FB. The counter is no longer a program. We're going to take that out of the task, and what we're going to do now is create ourselves a new program, and this we're going to call double counter. It has 2 counters in it. I'm going to make this a function block just to start out with, and I'm going to make this out of ladder. Now we don't recommend, we strongly recommend ladder only be used for what it was originally intended for, and that is relays and timers, discrete Boolean logic. So I'm kind of violating that rule right here just to prove a point on how easy it is to call one language from another language. So we'll make this one ladder. We'll say OK. Now if we want to put 2 counters in this ladder, so that we do that by just dragging our counter over to our rung and giving it an input. I can call this input anything I want. I'm going to call it increment. The auto declare comes up. I says I do want that to be an input. We'll give it a value of 2 for no better reason, and it is an integer. We say OK. I could give it a comment if I wanted. We have to give the name. We have to name and declare every instance. So we're going to declare this instance of the counter as a C1. The auto declare comes up, says, do you want that to be counter? Yes, I do. Now I'm going to show you something kind of odd. Our declarations for instances, we make those inputs, and I'll show you why we want to do that later on. All right, and so we just say OK to that, and then we have to assign an output to that, and we make that here. We give it an output of count 1, and count 1 will be an output, and it's an integer, and good. All right, now we need 2 counters, so we're just going to make a second, instantiate the second counter here, and we're going to give it a different name, and we're going to make this an input as well. This instance, we're going to give it a different name on the output, and we're going to make that an output. And then just for fun, let's say for some reason we wanted this second counter to increment by a different amount than the first counter. So let's say we wanted to increment by 1 more than the other one increments by. So we would, in normal ladder logic, we'd have to put an add block in there, and we'd clutter up our code. In the Bedrock IDE, we could just mix structured text and ladder. So we just go like that, increment plus 1. I could call a function here, sines, cosines, anything I wanted. I could make this expression as complicated as I want it, as long as it evaluates down to an integer. That's good. So we save ourselves a lot of code and complexity that way. Now I could go ahead and simulate this, but before I do, I want to just show you one more language, and this will be the continuous function chart. So we're going to call this, now this will be our main, our top level program, and we're going to use continuous function chart. Now CFC is a great language. It's graphical, sort of like ladder, but it's infinitely more flexible. You can place blocks anywhere you want. You can connect blocks together with nets or with names or with connectors. It's much more like LabVIEW or MATLAB Simulink. So it's much better language for top level, but it does still graphical like ladder. So in this language, we would just bring boxes in, and in this case, I could type in the name of the box I want, double counter, or I can go find it here, double counter right there. And then it suggests a name. I don't want to use that name. I want to use another name. Double counter 1, DC1, okay, and declare that as double counter. And then we're going to make inputs. We're going to make the input increment by 20 for lack of anything better. And we're going to call the output, the first one, count 1, and it's an integer. And the second one is going to be count 2. Again, I could name these anything I want. They don't have to be the same names. Now you notice the two internal counters are declared here as inputs. We'll use those later. I don't really want to see them on my top level diagram, so I can just go remove those, and they're gone. And there we go. And I can move everything around me. This is all full feature. It'll reroute itself, and I can grab everything and move it all around, and so forth and so on. So I can make very, very readable block diagrams basically of my program. We'll show you that later on as well. And I can simulate this. First I got to take my main, I got to drag it down and put it in the task there, and we log on. And now here it's asking me, do you want to log on with an online change or log on with a new download? I could do either one of those here. Online change will do a bumpless switch for the new to the new logic at the end of the next scan. Login with download does an automatic restart for me, reset, so that's the one I want to use right now, but I could do either one, it doesn't really matter. And then I can, just like I did before, I can hit the F9 key to set a breakpoint here. I can get it off and start it running. Here we've hit the breakpoint, there I can step over it, step into it, step out of it, and so forth. I'm just going to hit F8 to step in, and we'll go to our ladder logic, and then that'll jump into that first counter, which increments by 20, and it does that increment, it comes back out, and it assigns that to the output. Then we're to the next counter, and this one's incrementing by 21, remember, one more, and it does that increment, and it returns, and it assigns its output, and we're back to the top. And so again, I can turn that breakpoint off, and I can let it run free run, and I can even while it's running, or even not, I can still look and see what's going on inside, and I can go look at each instance of that counter within there and see what it's doing inside. Okay, so that's how easy it is to create a top-level program and create a couple function blocks that call each other in different languages. We'll show you the power of that when we show you the real examples at the end. Okay, now let's say that these counter and double counter, we want to make these functions and function blocks available to the entire company. First, let me mention that we could make these available to other devices within this project. So in a Bedrock IDE, you can program all the devices in your entire plant in one project. You can share objects amongst those just by dragging those down into this POUs view. So I could do that and share them amongst all my devices here, or I can put them into a library and share them amongst all my devices and the entire company. All right, so I could just copy these, cut these out of here and paste them, but what I'm going to do instead is I'm going to show you another feature here real quick. This is folders, so I can add folders anywhere I want in the hierarchy. I could add folders and folders and folders, whatever that helps me organize my design. Here I'm just going to make a folder called No Build, and the beauty of that is if I go in, and you saw me do this earlier, if I go in and I change the build and exclude it from the build, now anything I drag into that library, into that folder, is now excluded from the build. I do need to go offline before I do that. And there we go. Now notice that the main has a problem now because it can't find that double counter because it's gone. But we'll fix that momentarily. Okay, so I'm just going to go here and I'm going to Control C to copy those. And I'm going to go open up a new Bedrock project. Now you remember before we had projects and libraries. We chose the standard project last time. This time we're going to create a library, and it's going to be an empty library. Okay, and let's think about that for a minute, and then all we need to do is go in and paste our two objects in there and just say File, Save Project, and install into the repository. We'll say yes, and it needs a little bit of information, so we do Bedrock, and we're going to call it Gary's library, Gary's lib, and we'll start with a version 0.0. All right, and then that's all we need to do. Now it's building some tables and it's installing that into the repository. In this case, the repository is on my laptop, but it could just as easily be in anywhere in on your company server. It could be controlled, revision controlled through Subversion, or what have you. So everybody can get to it. So we're going to go back to our project. Now it's installed in the library repository, but it isn't yet made accessible to this project or this application, because you don't want every application to be burdened down with every library that exists in your entire library repository. So instead, what they provide for the Bedrock IDE provides the library manager. The library manager, we can just go in and we say add a library. We can find our library. Here it is, Gary's Lib. And we just say, okay, we install that. And boom, it's done. Now notice the main went away. The squiggly line under main went away. We can still simulate this just like we did before. Go in and I can now I compiled this or I created this library uncompiled so that the source code is still available. You have the option to hide the source code if you want, or leave it available if you want. So in this case, I can still double click on that. I come right in here. The only thing I can't do now is I can't change that. I can't edit anything that's in that library. So I have to go back to the library if I want to make any changes to that. So that's good. It provides good library control that way. But I can simulate this exactly the same way we did before, and it'll behave exactly the same as it did before. So we can just set a breakpoint here and just kick off our simulation and single step in. And we're single stepping into the library now, just like we did before. All right, now let's see what happens when somebody updates the library. So we'll go back into our library project here, and we're going to update the revision. So let's say we make some changes and we update the revision to revision 1. 0.0.1, and then we go ahead and publish it as we did before. Now when we come back into our project, if we were to open up this project, or if we just look at its environment, this dialog box will come up and indicate to us that the underlying library revision has changed. Now the Bedrock IDE has very tight revision control. If a newer library revision becomes available, the Bedrock IDE will give the programmer the option to update. So it's completely within the programmer's control now whether they want to update to this new library or not. So if you're going back and making a minor change to a project that you did 5 years ago, you don't want to risk any underlying changes to the libraries upsetting the behavior of your program in unexpected ways. Well, you don't have to update to the new revision of the library. Just keep with the old revisions. The revisions are stored, the revision numbers are stored as part of the project, so the project knows what revisions that was last used to compile to. So if you need some features that are in a library, in revision to the library, well, you can update just that one library and leave the other ones alone that you don't need the new features. Or if you're requalifying your whole plant, you got to go through the whole process anyway, well then you can just say set all to newest and say yes, okay, and it'll set all your libraries to the newest, and then you're ready to roll. So you notice here now the Gary's library is now at version 0.0.1, the new version. Now let me show you another library. There's a library in the CODESYS Store, and we'll talk about the CODESYS Store more in a little bit. The CODESYS Store has tons and tons of different libraries and functions and plugins and all kinds of things that you can access. One of those is called the OSCAT library. Now OSCAT is a group of open source library vendors, creators that create open source library elements for industrial controls. These people happen to be based in Germany. They have no association with CODESYS, except that they use the CODESYS development environment for creating their libraries, because the CODESYS development environment is IEC 61131 compliant, and it's free, so can't beat that. Now we can find this OSCAT, or you could search by different function names. It'll still come up with the OSCAT library, and there it is. And I already have it installed on my system, so I'm not going to install it again. But what I do need to do is I do need to bring it in and make it available. So we add library. I could go find it. I can type it here, whatever I want to do, and make that available. Now to use that library, so let's go back to main. And what I'm going to do now actually, before we do that, let me just show you all the things that are available in here. This thing just has tons and tons. The documentation, the PDF file is like 900 pages. It's just it's very well documented and has a lot of features in it. So we've got engineering, we've got process control, so it's got PIDs and filters and so forth, conversions. It's got measurements, it's got sensors, it's got signal generators of every type and imaginable. Signal processing, it has single pole, double pole filters. It has all kinds of logic, triggered flip-flops, counters, and so forth. It's got mathematics, it's got arrays, it's got complex math, it's got double precision, and all kinds of geometric functions and features. So it's a lot of capability here. What we're going to do is we're just going to use the counter out of the OSCAT library. And now I could type it in if I know the name of it here, or I could go find it. Now notice this now has an OSCAT library. So we can just navigate in here. I could search for it by name if I knew what it was, or knew what function it was, or something that was in the name. Either way, you can find it. Here we just want this counter BR. We'll just go ahead and call it counter BR as a name. It's an OSCAT library counter. Now, this one counter is a little bit different than our counter in that it does require a clock. It requires a signal going into it. So we're going to make our own clock. I could create a clock variable and put a not block in here to make a clock if I wanted, or I can just use this feature to make clock equals not clock. Boom, and clock is going to be a Boolean, and we're done. That's how simple it is. Now we can go ahead and simulate this just like we did before, and log in with a download. We'll look at our main program, and we'll kick it off, and there it's incrementing just like you'd expect it to increment. So that's how easy it is to bring in an external library and use those library objects. The OSCAT library also has a building library for building control. It's got boilers and thermostats and fans and blowers and those kind of things, and it also has a library for field bus devices to help you connect to your field bus devices programmatically. We'll show you that later on as well. Alright, let's talk more about the CODESYS Store. I gave you a little preview of that earlier with the OSCAT library, but we can go into more detail here. You can get to the CODESYS Store two different ways. One is through the IDE, clicking on the little shopping cart button here, or you can go directly to store.codesys.com. If you go through the IDE, when you download, it automatically installs the package for you, so it's one less step. If you go to store.codesys.com, download the package, then you come into Tool, Package Manager, and install that package. The CODESYS Store has many features and functions available to you, more than we have time to go through now, so I'm just going to go through a quick sampling of these. It has a number of examples. It has an alarm manager example, application manager that shows you how to programmatically manage your applications. It has a task manager to programmatically manage your tasks. So you can set tasks, you can set your watchdog timers, you can react to your watchdog timers and things like that. It has object-oriented examples to show you how to use object-oriented features. We'll talk about that more later on. Has a trend and trace examples. As far as add-ons, it has an application composer. This is for if you develop for developing repetitive type of applications. It has a profiler, static analyzer, and subversion integration. We'll talk about those later on. It has a package designer for creating your own package, and it has a MATLAB Simulink interface for interfacing to MATLAB. It has quite a large number of libraries. It has file utilities for reading and writing files on the controller non-volatile RAM. It has matrix libraries with matrix inversion. It has an OMAC PACML state machine. It has date and time libraries. It has libraries for accessing CSV, XML, and INI files, again, on the controller non-volatile RAM. And it has integration. It has integration into ePlan. So if you use that for designing your plant, it'll automatically bring in all of the tags and such from your plant from that. It also has other items you can buy, such as the license for the control win. The one I'll show you shortly runs for 2 hours before timing out. You can extend that to indefinite if you want. And then it has quite a number of add-ons and examples for the CODESYS visualization tool. It's HMI that we'll talk more about later as well. The Bedrock IDE makes easy work out of setting up a full preemptive multitask environment. We'll demonstrate that by making a copy of main here, and we're going to call this slow main. All right, and then we're going to create a new task, and we're going to call this slow. All right. Now this brings up the task configuration. We can set the priority on the task, so higher priority tasks will interrupt lower priority tasks. We can set what type of task. It can be cyclical at a certain time period, event driven. If a Boolean goes true, the task will get executed. Freewheeling, it just runs as fast as it possibly can, and status, it runs when the Boolean is true. Since this is our slow task, we're going to just make this one 200 milliseconds. We can also set a watchdog timer on every task, and we can also set a sensitivity on that watchdog timer. The sensitivity is useful, for instance, if you have a program that has a lengthy initialization routine, you can set the sensitivity so that the watchdog timer will ignore the first time that that program is run, so that the initialization routine doesn't trigger your watchdog timer. And then to bring a program into the task, it's as simple as just dragging it and dropping it in like that. So we'll go online now, and we will tile the slow task and the fast task together, the regular task together, so that you can see them run side by side. We'll kick them off, and you'll see that the slow task is running much 110 times slower than the fast task, as you would expect. Now the task manager does have a status, so you can watch exactly how long your tasks are taking to execute, how many times they're executed, the maximum cycle time and the minimum cycle time, the amount of jitter, maximum jitter and minimum jitter. We got quite a bit of jitter on this because we're running it on the controller that runs on the PC, and of course the PC is running a lot of other things, so that's why you're seeing that. You don't see nearly as much jitter when you run it on the controller. So that's as easy as it is to set up a multitasking preemptive environment on the Bedrock IDE. So let's talk about data structures. So the Bedrock IDE fully supports data structures. We can create data structures, and let's clean things up a little bit here and create ourselves a data structure. In the IEC 61131 language, a data structure is known as a DUT. And in the Bedrock IDE, we can create structures, enumerations, aliases, and unions. We'll create one called counter data type. Okay. And then just to save ourselves a little time, I'm just going to copy some of the data out of this counter and make it into a data structure. All right, and so notice I can have initial conditions in data structures. That's perfectly acceptable. So we'll come back to our main, and we'll create ourselves a instance of the counter, and we'll just call it C1. All right, and now we can, in the bad old days, say we want this this counter data to be accessible to an HMI. So in the bad old days, we would make a very lengthy HMI tag here with all the information kind of encapsulated into it. So we'd probably call it counter underscore C1 underscore increment underscore, I don't know what else. Big, long, flat, back in the old flat days. Well, in the 90s, they came along and they finally gave us data structures. So we were able to encapsulate this data a little bit. So we're going to create an instance of the data structure here. We're going to call it CD, and we're going to make it of type counter data, and then I can just hit control space here to fill that in for me. If just makes things a little simpler. So here I just can give it CD dot increment here, and here I can give it CD dot count. Okay, so now we've been able to encapsulate now this data into this data, all the data for this counter into this data structure CD. So now I could access that in my HMI just by sharing CD. However, in the Bedrock IDE and IEC 61131 has actually made data structures almost obsolete. We really don't need to do this anymore. We can still access all the data within this data structure just like we would expect to be able to. CD dot using the dot convention dot count will give us that data. However, that's really not necessary anymore because in the IEC 61131 and in the Bedrock IDE, we can actually access the data directly and using the instance name as the data structure. So instead of saying cd.count, I could just say c1.count. It'll give me the exact same information there without having to copy all this data into and out of data structures. I just access it directly. Even more interesting, I can come in here and I can actually drill down in. So let's look it up at here in DC1 dot, and I can get to its internal counter, and I can get to its count within its internal counter. So I can actually drill down in, and now you notice that's why we declared our C1 and C2 as inputs. That allows us to do this type of drilling in here. So this is how we are able to access connect HMI faceplates up to Bedrock function blocks directly with just a single instance name. So in other words, I could have a faceplate for this double counter that has both counters in it, and who knows what else below it, motor controllers, whatever. I can make that entire connection of potentially hundreds or thousands of tags. I could make all those connections with just this one instance name, DC1, and then the HMI, the faceplate, would then drill into those and connect up to all those individual tags that are within there. So instead of the bad old days when we had 1,000 or 10,000 flat tags, or maybe hundreds of data structures, instances of data structures, now we don't need any of that. We can just go directly into the instance itself and connect. And I'll show you that towards the end of the demo today. Now we can even use instances of function blocks as data structures themselves. So I'm going to bring over a selector, and what this does is this allows us to extract members of a structure. And so here I'm actually going to give this now. I'm not going to give this a structure name. I'm going to give it the name of a function block, but I can still use this. So I can still come in and say CD, and now I'll get my count and my increment out of there. Now the Bedrock the CODESYS has a little bit of a bug here. It won't display these values unless I actually assign them to something, so we'll just do that quickly. And then I can go online here, and we can run this, and we can see that here we're seeing CD count. So this is actually reading the value out of this data structure, or we can access this output directly with just C1 count. They're the same. Or we can drill into this one and find its value of its counter here, and with DC C1 count. Or we can use the function block itself as a data structure and look at its members directly. Now we can use, there's other uses for data structures. One of those is composite pins. I'll show you how we can do that real quickly here. So I'm just going to make a copy of counter and put it in here, bring it back here. I'm going to call this, I don't know, for lack of anything better, I'm going to try to call it counter X. Alright, what I'm going to do in counter X now, instead of having these inputs and outputs, what I'm going to do is I'm going to make a output. We're going to just call it data out, and it's going to be of type counter data type. Alright, and I'm going to do the same thing on the input. So these are now, we'll call it data in. So now the inputs and outputs are now data structures. Okay, and we've got to come down here and update our variables a little bit here. So we have the structure. There we go. All right. Now I'm only using data in here. Obviously you'd use data out if you were doing a real example here, but I just showing you quickly how this works. All right, we'll go back to our main here now, and we'll make an instance of this counter X. counter X, and that name is fine. And we'll make another one, and we'll just rename this one, give this a new name, and call it 1, and that's okay. So, and then I can connect these together, and here I can actually make this, just connect that there. So now I can connect these blocks together with these composite pins and composite connections. So I could make, complex data structure here. I could have a data structure of a data structure of a data structure, complex data structure, passing a large amount of complex data between blocks in your continuous function block. So it just shows you how you can really use composite pins to clean up your continuous function blocks. Okay, I want to show you one more use for data structures, and this is for mapping to field devices. So I'm going to come in here, we'll add a new device to our 4.E universal field bus controller, and we're going to make this a Modbus device. So this will be a Modbus master. Okay. Then to that master, we will add a Modbus slave, and we'll configure this slave with a channel. We'll add a channel here, and this is going to be our read channel, for lack of anything better. Say we give it a length of 100. All right. Now, when we go down to mapping, see, we would have to normally map every one of these words individually, but there's a better way to do that. So first we create ourselves another user-defined type. We're going to call this ABC123 vars. Okay, so this is a fictitious Modbus device called ABC123, and it's a structure, and this then maps to the data that the Modbus device is giving us. So, we could have I don't know, status is a bool, error or messages, we'll call it, could be a string of 10 words. We could have RPM, which could be an integer. We could have current and voltage, which are real numbers, and so forth and so on. So anyway, this is just an example of what the mapping might look like coming from that Modbus device. So what we need to do is now we somehow need to get this block of words into this data structure. The way we do that is we create another data structure, and this is called a union. And a union is like a structure, except all the members share the same memory space. That's a great way of doing what the C programmers would call a typecast. And so we do that, we create this. We have two members here. We're going to call one vars, and this is going to be ABC123 vars. And the other one will be what we use for mapping. And this will be an array, and we have to have 100 members here, 0 to 99. And this is going to be of words. So this matches the mapping that you saw in the Modbus device. Okay, give that a semicolon. All right, so now all we need to do is we come into our main here, and we create ourselves an instance of our new union. So we're just going to call this ABC123, and it's of ABC123 type. Okay. All right. Now we come back, and for our mapping here, all we need to do is up here we just go ABC. Well, we can navigate to it if we want. Might be easier to navigate to it. Application, main, ABC123, map. There we go. So we've mapped that data structure now to the whole mapping. So all these 100 words now are mapped into this data structure. So we need just one variable there. And then to use the variables, the resulting variables in our main program, so we just need to come and in here now we just do ABC123 dot vars dot, and so if we want to get to the RPM, we get to the RPM, just like that. So that's as easy it is to map Modbus devices into real variables. Now, if the Modbus device doesn't follow the rules, if it uses the wrong end in or it puts padding in or such where it shouldn't, there's more you need to do then to fix those, and we have a way of doing that as well. So just give us a call and we'll show you how to do that. So next we'll talk about parameters. The Bedrock IDE provides a powerful method for saving tuning parameters back into your project. So let's just come in here and to counter X for any lack of anything better, and say that we have some parameters here. What we're going to make these, it's going to be a var input, and then we'll use this keyword constant. And on anything we put in here, RPM, whatever, then it shows up as constants. And let's go back to our main, and we'll update one of these. You'll notice now that this block has this button here for parameters. So that allows me to come in and set my values on these parameters. So let's just say I want this to have a value of 5. Okay. Now we go online with this, and so this is say we've set our our parameters for our PID loop, say at what we think that they might be. So now we're online and we're going to tune our PID. So let's say 5 didn't give us exactly what we wanted, so we're going to try a value of 6 instead. All right, and we're going to do the old Control F7 to write that. So now we're actually running our plant with the value of 6. And we say now, okay, this is what we want. This is the proper value for this. All right. So what happens now, and when we go offline, you'll see there's a little star there that says that this parameter value has been changed while online. So we can just come in here and we can say save the prepared value to the project. See, so the original value is 5. The value that we used during the live run was 6. And here we just say saved this prepared parameter. And now 6 becomes the permanent value for that RPM. So this becomes part of the project. If we do a full download again, the tuning parameter 6 will now be a permanent part of that project. Let's talk about OPC-UA. There are 2 ways to expose the Bedrock IDE variables and objects to an HMI via the Bedrock's built-in OPC-UA server. The first is to use attributes. So we're going to drag the counter out of our no build here so I can modify it without going back to the library. And so I'll show you the first way is you can expose your variables while you're writing your function blocks. And you do that by means of this feature called an attribute. And it's the attribute is symbol. And that can be equal to either read, write, or read, write. Okay, so now I put this attribute in here, and now with it at the top of the function block like this, it will expose all the variables within that function block to the OPC-UA. I could put this attribute just above each variable, and then it would only apply to that variable individually. All right, and then so next we need to create ourselves a symbol configuration object, and we want to support OPC-UA features because we are OPC-UA. And in here we have to do a build that allows the compiler to gather up all the variables and so forth. And so then we'll come in here, and the first thing we'll notice is that the counter, both in the instance of the counter that we have is grayed out, and it's already exposed via attribute. That's the attribute we talked about. You can go in and you can find out exactly what is exposed in there. Both the count and the increment are both exposed. The other way is to just click on the object, and then it will expose everything via this mechanism. And we can change. We can make it read only. We can make it write only, or we can make that read. And we'll show you how we can expose DC1 and look at all its levels of hierarchy here as well. All right, so next we need to simulate this now. Since this is actually communicating with the outside world, we can no longer use our internal simulator. We now need to use the runtime that runs as a service under your Windows. We do that by going over here to Start PLC. Then we have to do one extra little step here, and that is to scan our network for that runtime, and here it is. and select that. Now this is exactly the same way that you would method that you would use to connect to actual hardware. So if we had actual hardware here, you'd see another line here that says Bedrock SCC, and we would connect to that. But we're going to connect to the internal runtime for now. All right, and then we log on same way we did before, and we just tell it we'll get it started up and running here. And then what we can do is we can go to any OPC-UA browser that we want. We can go find our Bedrock, the full-featured controller that's running on our laptop, and then we can go and find our variables. Now notice two things here unique to OPC-UA and are infinitely better than the bad old days. First of all, I can browse. The OPC-UA has this browse feature, so I can browse all the symbols that are exposed on the OPC-UA server. And the second is, notice that the hierarchy is still maintained here. All the hierarchy is still here. So this is the features that allow us to be able to make a single connection to thousands of tags within the Bedrock IDE. So for instance, if I had a faceplate that needed all these instances, all this information in this hierarchy, I could just then connect to it all by just saying DC1. I could connect to this entire faceplate through just saying with a single DC1, and then the faceplate would know the hierarchy below that, and it would make all those connections below that. So anyway, I can look at anything that I want here. So that, in a nutshell, is OPC-UA. We'll show you a little bit more of that shortly when we show our discrete batch and continuous demo. Next, let's talk about data sharing peer-to-peer between Bedrock controllers. Now, if you have Bedrock controllers set up as remote I/O, daisy-chained up to 10 Bedrock controllers and SRCs, those variables all just appear flat on the top level. You can't tell that they're not local to your backplane. So that's not what we're talking about here. We're talking about if you have a system where you have two Bedrock controllers peer-to-peer, two or more. You could have hundreds, whatever, but they're set up peer-to-peer, not daisy-chained in a remote I/O using the SRCs. So to demonstrate this, what I'm going to do is we'll just go back offline here, and I'm going to create a copy of this device. This will demonstrate a couple of things. First, it'll show you how you can manage multiple devices in the same project. So this is how you would typically, if you have a plant with 10 Bedrock controllers in it, well, you'd have 10 devices here in your project. It's best to manage them all in the same project. All right, so what we're going to do is now, to be able to demonstrate this, I need to kick off a second controller running on my laptop here, and that's just easy by going here and going Control Win. That opens up a second runtime running in this terminal window. And so what I'm going to do, let's just do some names here. So this is going to be controller 1, and we'll just call this controller 2. Hopefully you would come up with more creative names than that. And we're just going to go ahead now and get controller 2 kicked off and running. And so to do that, we need to scan the network. I'm going to assign it to the first controller out there, and we're going to just get it running online here. And there we go. It seems to be running. And now what we're going to do, so let's go back to our controller. For controller 1 now, say controller 1 now needs some information from controller 2. First, we make it our active application. You can only operate on one active controller at a time. So here we're going to start to work on this one, and it needs some information from controller 2. So in the bad old days, of course, we'd have to go down to controller 2, we'd have to expose some variables, we'd have to come up to controller 1, we'd have to instantiate a client, get those variables, or do produce, consume, and that kind of thing. So the Bedrock IDE makes this infinitely easier. So now all we need to do is we add a device, an object called a data server. And within this data server, we add a data source. And since now we only have one other controller, so that's our only other data source now, is an application within controller 2. Obviously, if we had 10 controllers, we'd have 10 choices here. But this is our only choice. We come in and we say add that. And then what that does is brings up this this box dialog, which allows us then to go in and choose what variables that we want to access off of that other controller. So in other words, the device that needs the information or wants to provide the information is the one where you decide what information that you want. So I don't have to go down here to controller 2 and do anything at all. Just up here where I want to use the information, that's where I specify. Now notice also here we can share data types. So that's a very handy feature. So if you have want to bring over some complex data from another controller and you want to be able to use its data structure, you can also bring over the data structure that goes along with that. So anyway, so we've got this selected now, and so what I can do now is I can go back to my main, and you'll notice that we have, if I go in and browse now, I have a new category here called controller 2. And so I can go in and I can select that count 1 from controller 2. It gives it a full path name. Now I can go online. I have to come in here and I have to scan for devices, and I'm going to assign this one to the second controller, and we'll get it kicked off and running. And then we will tile the two windows side by side so that you can see. Let me get this one started. All right, so now we have, let's just clean this all up. We'll go to our main here, and we'll go to our main here, and we'll tile those two side by side, and we'll scale down on this one so that you can see that the count 1 from controller 2 is the same here. So that's sharing that data. So that's how easy it is to share data amongst peer-to-peer Bedrock controllers. The Bedrock IDE provides a built-in full-featured digital storage oscilloscope that runs directly on the controller hardware. This is not a trend through the OPC-UA at some subsample rate. This actually runs on the hardware at the same scan rate as your hardware. It provides all the same features you'd expect from a DSO, except you don't need to hook up leads or charge the battery. A trace can be set up to trigger on a difficult to find intermittent problem and then run free for months or years waiting for that problem to occur. Once the problem does, a preset amount of data can be stored before and after the trigger event. The IDE does not need to be logged in for the DSO to run. The HMI can be configured to indicate when a trigger has occurred and page you or send you a text message or something. And then you can log in at your IDE and look at the data before and after the event to help you diagnose why that event occurred. So we'll demonstrate this quickly. First we set up add a new device on object, and this is going to be called a trace. All right, and we configure that trace. So we're going to configure, say that we've got in a situation where count 1 is wrapping around and that's causing an upset in our control. And it only happens once every 6 months or so. So what we want to do is we want to trigger on that. So we're going to trigger on count 1. Nope, not on controller 2. Sorry. We're going to go do it on the local controller. Application main count 1. Okay. And we want to store 25. Well, first of all, we want to do that on the negative edge so we can see when it wraps around. We're going to store 2,500 points before, and we want to trigger at 0. And we're going to make this our main, associated with our main task. And we want a total of 5,000 points. We want 2,500 before and 5,000 after. Okay. And then just to make this more interesting, I'm going to go into main task, and I'm going to make this run much faster, just to show you how fast that we can actually capture data on this. All right. So then the next thing we do is we add a variable, and we will add that count 1. And we'll also add a variable. We'll also add the that clock that we created earlier, just to demonstrate. Now we can do things here, that we can set the x-axis, or we can leave the scaling. We can change the scaling. We can leave it auto scale. We can make it different types of points. We can do what type of line. We'll make these step lines and so forth. All right. So now what we do is we will go and we have our trace all set up and ready here. And so what we will do is we'll log on to our controller as we normally do, and then we will what we'll do is we'll set off our trace running, and then we'll start up the controller, and we'll log out. So here, let me just demonstrate. So we'll get the trace running. There, it's running in real time. We'll start our process. Now we've logged off and we've gone home for the weekend or the month or whatever. 6 months later, we get a page on our phone. We come back. All we have to do is log back into our controller, and boom, there our data is before and after the trigger. So here we triggered on the wraparound, and here we can zoom in and see exactly what happens exactly before and after each the trigger. And then we can drop down cursors here so we can see, we can prove to you that we are really sampling at 2 milliseconds right here, 2 milliseconds rate. And looking, we can see exactly what happens. We'll look at values and so forth. That's just a small sample of all the features that are available on the Bedrock IDE trace. It's a very powerful feature. I use it often for diagnosing my code. We'll show you some examples of that later on as well. Alright, now let's talk about object-oriented programming. The Bedrock IDE fully supports object-oriented programming, including encapsulation, polymorphism, inheritance, and interfaces. Object-oriented programming allows base functionality to be enhanced without copying that base functionality. In this example, we'll extend the functionality of the counter with 2 and 3 versions of the counter. Now, counter is kind of a generic example here. Think more of like if you have a skid with pumps on it. You have a 1 pump skid and a 2 pump skid and maybe a 3 pump skid. How you can extend that functionality of that 1 pump skid without duplicating that code that's in your 1 pump skid. So we're going to use, as I said, we're going to use a counter. So we're going to make a copy of the counter here, and we're just going to call it counter 1. All right. We'll go into our new counter 1 here, and we're going to just make some minor modifications here. We're going to make count to count 1. All right. Now we're going to add a method onto this counter. Methods are, you can think of these as local functions that are local to this function block. They share all the same data as the function block. They can be private to the function block, so only the parent function block that owns that method can call that method, or they can be public, where anybody can call that method, or it can be made such that there's the access specifiers, or it can be protected or internal, where only derived classes can access that method. So lots of options here. So we're going to make a method. We're going to call it reset. We're not going to give it a return type. We don't need a return type. And in this, we're just going to set our count to 0. All right, now notice the auto declare didn't come up. There's no squiggly lines. I haven't declared count 1 here, but it is declared because it's using the count 1 that's in the parent here. Now I can declare variables here. However, they're only valid during that call. So just like any other function, you can create local variables, but they disappear after the end of the function call, and they're reinitialized to their initial condition at the beginning of every function call. All right, so now let's say we need 2 counters here. So I'm going to make a copy of 1 counter. We're going to call it count 2, counter 2. Now, so in the bad old days, what I would do is I would just now add additional functionality onto this counter 2. So I'd add another count to this one. I'd duplicate all the functionality in counter 1 and add to it in my copy counter 2. Well, that was the bad old days. So now, instead of doing that, all we need to do is extends counter 1. Boom. Now we have this function block, counter 2, has access to all the variables and all the non-private methods of counter 1. So first of all, we don't need this counter 1 anymore. We need counter 2, and we don't need increment at all, because that's declared in the first. That's declared in counter 1. I mean. So we'll just update these to counter 2, count 2. Now, what we also need to do, if we want to completely replace the functionality of counter 1, we just did that. If we want to also include the functionality of counter 1, we use the super pointer to get the access. So now once if we instantiate counter 2 and call it, this will be executed, this count, and then super will be executed that will go in and execute what's in its base class. Same thing with the reset. We need to change this to count 2, and we also want to call its base class reset as well. So this is we use a super pointer dot reset. Okay, so now if we call the reset on counter 2, it'll execute this, which will reset the count 2, and it'll use the super pointer to get to the base class reset and reset that. All right, let's just do this one more time. We're going to make it count 3, counter 3. All right, we're going to go in there. We're going to have it extend counter 2 and 3 and 3 and 3, and go to its reset and change it to 3. All right, so now we have a family of counters. We have 3 counters, but we haven't duplicated any code in any of these counters. If we add functionality to the counter 1, that functionality will automatically be available to all the other counters. If we add additional methods to counter 1, all those base class methods will also become available to all the other methods. Standard object-oriented programming. All right, so let's see what this looks like in a real example. So we're going to go to our main, back to our main here, and we will create an instance of first counter 1. And we'll use the name that it recommends. That's good. We'll get an increment of 1. And we'll instantiate an instance of counter 2. Now, just because I have derived off of counter 1, I've derived counter 2 off of counter 1, doesn't mean I can't continue to use counter 1. I have a 1 pump skid. I can continue to use my 1 pump skid. And we'll go to counter 3. Counter 3. Use its name that it recommends. That's fine. Give it an increment of 3. Okay. And now let's instantiate an instance of the counter 3 reset as well. And so this will be counter 3 dot counter 3 dot reset. Okay. Now we need to give it the same name as above. Counter 3 underscore 0. So this is the reset method for this instance, counter 3 underscore 0. Now we don't want to reset on every single scan, so we're going to add an enable to this and just call that enable. All right, make that a bool. Okay, so there we have our 1 pump, our 2 pump, and our 3 pump. All right, let's go online and get this running, and things are counting as we would expect them to count. Now let's go ahead and change do our reset. And so we reset the reset for instance 3. It goes in, resets counter 3, then resets counter 2, and then calls the super pointer and resets counter 1. Everything resets as we would expect. All right, now let's go and let me show you something. We're going to go in and we're just going to disable this reset on the 3rd counter, and we do that by excluding that from the build, so it's gone. But notice that no little red lines show up here, even though we're calling the reset on counter 3, which doesn't exist. It's perfectly happy with that, and that's all a technique of object-oriented programming. So if the base class functionality is adequate and we don't want to change it, we don't have to. We just don't define a reset, and it will automatically use the reset of the derived class. So here, if we go ahead and go back online again, and we'll get it kicked off and running. So everything's counting as we expect. But now, if we go and reset, notice that the count 3 doesn't reset anymore, since we don't have that count 3 equals 0. It doesn't exist. But the other two continue to reset. The base class functionality continues to exist. just as we would expect. The Bedrock IDE also supports other object-oriented features such as interfaces and unions. You can read more about those in the online help documentation. The Bedrock IDE provides an object for managing groups of persistent variables in the form of recipes. Any variable of any type, including complex user-defined types or even function blocks, can be stored as a recipe. Recipes can be created, and a set of values for the variables can be designated for each new recipe. So let me demonstrate this. First, we add a recipe manager object, and to that then we add a recipe definition. And to that we have to say what variables we want to use, we want to store as our recipe, what variables we want to be persistent with our recipe. I could pick any variables here. I can actually pick an entire instance of this counter, and that will go and get the variables for its inputs and outputs, which we have here now. I don't really want to care about increments, so I can just delete that one. Now I can create recipes. We'll create a recipe called regular. And this will give values of, we'll just give this all zeros. So we'll kind of use this as a way of resetting our counters. We can create more recipes. We can make a recipe that's spicy. And this one we will just reset to 3000, 2000, and 1000. All right, now we can go online and start off the simulation, and the current values will then increment as we would expect them to. So these are our current values. We can also set minimum and maximums, have comments and so forth. We don't need all that space. So here's incrementing as you would expect these variables to do. Now at any point in time I can write this recipe, which causes zeros to all be written into those variables, and then they continue counting. I can write this one, which causes them all to start out at 3000, 2000, and 1000. I can create new recipes. We can call this just XXX for lack of anything better. And then I can take and read the current values into those at any point in time, and they get written in there, saved. These are all saved in a file that's on the controller, so if you do a power cycle it will come back up and start off at the last recipe that was active, that was saved. All the values can also be read and written into files on your local hard drive, so you can create recipes from some external source and then read them into the Bedrock IDE and use those recipes. And all of this can be done either manually, as we're showing here, or programmatically through the recipe library function. We'll show you that when we show you the demos at the end of this. The Bedrock IDE provides a means to create users and groups and assign group permissions on every object and every of the thousands of actions within the Bedrock IDE. So let me show you that real quickly. So everything has properties and access control. So every object within the Bedrock IDE, so here I'm just controlling the entire controller and saying who can modify, view, remove, or add children to that controller. Every object within here, this function block, I can set its same properties. Access control, I can give you permission to certain groups to view, modify, or remove that object. Same with all the objects. Plus, the Bedrock IDE provides a method to control all of the commands within the entire IDE. So here's a list of all the commands in the Bedrock IDE, and individual permissions can be granted to each one of those. So for instance, online download, you can specify who can download programs, or online login. You can specify who's allowed to log into a certain controller, who's allowed to start and stop the controller, who's allowed to change programs on the controller. Basically everything that can be done in the Bedrock IDE can be restricted to certain users and certain groups. The Bedrock IDE has many other features and functions that we don't have time to cover in a 2-hour demo, but let me just run through them very quickly. We have an alarm configuration manager for determining critical process states and unusual event sequences. We have an external file, which is similar to OneDrive or some other synchronized directory tool. This allows files to be maintained in 3 places: in the development computer, in the Bedrock IDE project, and on the controller itself. If there's a change of this file in any of those 3 locations, then there'll pop up a menu to allow the file's contents to be synchronized between those 3 areas. And once the file is on the controller, then you have read-write access to that from your application program. So that would be another way you could do recipes or something along that line, get external information into your project and make it persistent. We have persistent variables. This is an easy way of periodically storing a set of variable values that will be retained through power cycles of the controller. We have POUs for implicit checks. This allows programmers to determine exactly how the application should behave in the event of a divide by 0, exceeding an array bounds, or some other error condition. We have a redundancy configuration is used to configure redundant controllers. Text to list is to provide a message in multiple languages for OEM, typically for OEM applications. And then visualization is CODESYS HMI, which is good for engineering screens and such, but it's not in the same league as Ignition. To absolutely squeeze every last ounce of performance from a Bedrock IDE application, you can add the CODESYS profiler to your Bedrock IDE. This allows you to know exactly how long every step in the application code takes to execute. It will provide the time for a function block to execute and every function block that function calls takes to execute, as well as how long each line of code in your program takes to execute. This tool will point out and let you correct every bottleneck in your code. The Bedrock IDE supports Python scripting to automate repetitive development tasks. This allows you to create macros and execute them from within the IDE or when the IDE is invoked. For instance, you could have a button on your HMI that invokes the Bedrock IDE and brings up the control code that is applicable to that screen. The Bedrock IDE makes it possible and encourages users to create their own libraries and place them in the CODESYS Store as a source of revenue. The online help document has many examples and guidelines for developing your own apps and libraries. The Bedrock IDE is fully integrated with Subversion. Subversion is the most popular revision control and collaborative design tool in the software development world. This isn't a simple project revision control system. Subversion is integrated directly into the tool, providing revision control down to the object level. Individual objects can be locked, checked out, checked in, or worked on in parallel. The system will merge changes to the same object down to a single line of code. The system keeps tracks of previous project releases so that old projects can be recreated at the touch of a button. Subversion can be run from a central server, allowing worldwide design collaboration. Alright, now let's talk about what we can produce with all these features and functions that the Bedrock IDE provides. But first let me brush off my high school drama training and put on my best Morgan Freeman accent and imagine the theme from 2001: A Space Odyssey going on in the background here, and bear with me. So in the beginning, there were relays and timers, and they were okay. Then came PLCs, and the people rejoiced in being freed from the bondage of hardware while keeping their native tongue and the language plant technicians were most familiar with. Then a growing discontent came over the land when ambitious and creative industrial control system programmers desired more advanced tools to write structured, scalable, and maintainable programming. But the masses were thwarted by sluggish and uncreative controller vendors who were too lazy to update their tools to modern standards. These overlords told the people to make do with ladder logic, so the people did the best they could with the meager blessings bestowed them, and devised clever workarounds to use ladder logic for purposes for which it was never intended. Then the IEC appeared before the people and exclaimed, "Follow me to the 61131 Promised Land, where you will be blessed with manna and standards to efficiently create highly structured, reliable, maintainable, scalable, and understandable industrial controller application programs." The people shouted, "Alleluia," and the waters parted to allow a mass exodus from their tools of the last millennia to the promised land of IEC 61131 and the Bedrock IDE. Seriously now, the Bedrock IDE is not your father's programming tool. Much like the Bedrock hardware, the Bedrock software was designed from a clean sheet of paper without dragging along 40 years of legacy. It is designed to meet the industrial controls programming needs in the 21st century and to be a familiar environment to the next generation of industrial controls engineers now coming out of college. For many years, ladder logic was the only available industrial controls programming language. As industrial controls programmers began looking for scalable, structured, and hierarchical programming techniques, trying to implement these in ladder was their only choice. Because of that, ladder was recruited into areas where it was never intended to be used and was poorly suited. The Bedrock IDE and IEC 61131 has solved these problems. The Bedrock IDE is based on modern programming methods and leverages the knowledge of the 20 million software programmers in the software world outside of industrial controls. It's designed to provide a highly productive environment for creating high-performance, reliable, and maintainable industrial software. While the IDE is easy to use, there is definitely a learning curve involved for engineers transitioning from older paradigms. Formal training is strongly recommended. You've seen all the 21st century features offered by the Bedrock IDE. Now let's see how they can be combined to make a design that is much easier to develop, very easy to maintain, and very understandable by plant technicians. Bedrock has developed discrete, batch, and continuous process projects to demonstrate the capabilities of the Bedrock IDE in real-world designs. We will start by showing the discrete view, but you will see the same techniques applied in batch and continuous. It's no longer necessary to train your engineers on 3 different ways of programming. IEC 61131 and the Bedrock IDE do it all. Looking at the discrete design, you will first notice the design is organized with folders. As mentioned earlier, folders can be added at any level of the hierarchy. Notice also that the design only has 2 tasks. Unless your process has a need for different scan rates, Bedrock recommends 2 tasks, one for the control and the other for the simulation. And to best simulate the asynchronous nature of your plant, the simulation task should run at a much faster and non-integer fraction of the scan rate of your control. With only one control task, it's easy to find the top level program. Simply double-click on the program in the control task, or you can find it in the main program folder. The top level is what Bedrock calls the plant view. This is a hierarchical view of your plant. In this case, the plant consists of an elevator, 3 conveyors, and 2 offloading stations. If the plant is large or complex, there may be several layers of plant and subplant views. In this case, there's only one plant view layer, and the next level is a detailed equipment view. Notice that this plant view uses composite pins to make all the connections between the blocks and includes status information to show the status of each piece of equipment. Pushing into the elevator block in the plant view reveals what Bedrock calls the control and equipment view. Bedrock recommends the control and equipment view for your designs. The control and equipment view places the input equipment on the left, the control in the middle, and the output equipment on the right. In this case, the input equipment consists of proximity switches, and the output equipment consists of motors. Pushing into any of these blocks reveals the detailed controls designs. The input equipment is simple. It consists of logic to allow the HMI to override the input. If these were analog sensors, they could also include scaling. The output equipment consists of the motor control logic. Since this is all discrete Boolean logic, ladder is a good choice of language. Notice how simple it is for plant technicians to use the plant view and control and equipment view to troubleshoot his or her plant. The technician gets a report that the in-conveyor motor for the elevator module is not running. He or she goes to the plant view to find the elevator, or uses the device tree to navigate there directly, then examines the elevator control and equipment view to see if the in-conveyor motor has been commanded to run. If so, then he or she pushes into that motor control logic to determine why the motor isn't running. If not, then he or she pushes into the control to see why not. The same troubleshooting technique applies to both batch and continuous process examples you will see later. The plant technician only needs to learn one troubleshooting technique for all types of plants. Pushing into the elevator sequence block reveals the sequential function chart that runs the elevator. The sequential function charts are ideal for designing state machines and state-driven processes. SFCs consist of a series of steps, transition, and branches. The current step is in blue and will remain in that state until the transition becomes true. Transitions can be simple Boolean expressions or complex ladder or structured text blocks. Branches can be sequential, where only one branch is executed at a time, or simultaneous, as shown here, where multiple steps can be running concurrently. SFCs allow for entry, active, and exit actions. Entry and exit actions only execute once when the step is entered and exited. Active actions are executed every scan while the SFC is in that step. Only entry actions are used here. We can push into these to reveal the code below. In this case, the code sets the state variables that are appropriate for that step. Using an SFC allows a technician to quickly determine the state of the machine and to determine why it's not moving on to the next state. For instance, the in conveyor may be stuck in idle because the elevator down proximity switch is not functioning. This is a great example of Bedrock's power to use the best language for the purpose. A beauty of the Bedrock IDE is that the exact same control design technique used for discrete can also be used for batch and continuous process. No need to train engineering and plant technicians 3 different design and maintenance techniques. This can be demonstrated by looking at the batch reactor design. Notice the C&E view for the reactor looks very similar to the discrete example. Input equipment on the left, control in the middle, and output equipment on the right. The input and output devices are basically the same as the discrete example. The only difference is the reactor sequence control. Just like discrete, a sequential function chart is the best tool for designing and maintaining the sequence portion of the batch process design. In this case, the system goes through the process to fill the tanks, add the necessary amount of ingredients, heat and agitate, and then empty the tank. Notice in this process, the recipe management is handled in the second step. You will see later on how it's managed at the top level. Just like discrete and batch can be programmed to the same tools and techniques, continuous process can also share those same tools and techniques. The continuous process example consists of 3 continuous reactors. Also notice in this case the recipe management is handled at the top level so that all the reactors are controlled by the same recipe. The recipe is controlled using the calls to the recipe control library elements. The recipe block outputs all the available recipes for the HMI to read and then accepts the desired recipe from the HMI. The ingredients values are actually read into the reactor state machine at the appropriate point so that the ingredients aren't changed mid-batch. Pushing into any of the reactor blocks from the previous slide shows the control and equipment view for the reactor. This looks very much like the same view for the batch process, except the inputs and outputs are now analog and the motors and augers are now variable frequency drives. But the control is now quite different. For this process plant, the control consists of a small state machine to run the startup, shutdown, and recipe changes. It then contains floor blocks to run the control loops for the tank and the 3 auger variable drives. The startup and shutdown sequence is implemented in sequential function chart as you would expect for any such state machine. The primary difference is the state machine spends most of its time in the run process state. Pushing into a block for one of the auger drives shows a custom block to compare the pulses coming from the auger motor encoder against the expected pulse rate for the current liquid flow rate. Being mostly mathematical, the compare is best designed in structured text as shown. Note that the structured text is shown in the run mode with all the current variables displayed. It can be displayed in the offline mode to be clearer to understand. The control block continues with 2-pole low-pass filter from the OSCAT library to filter the pulses and a PID from the OSCAT library to control the process. The control block also includes a control loop analyzer from Bedrock that can be used to analyze and tune your control loops. It will show where the poles and zeros of your control loop lay, as well as a control loop gain and phase margin. A trace can be used to monitor the results of the simulation, and/or simulation models themselves can monitor for the expected behavior in a fully automated test system. In this case, the light blue represents the flow rate into each reactor, the red indicates the liquid level in each reactor, and the yellow indicates the rate of an auger motor feeding ingredients into the reactor. The top four traces shows the handshake signal while the reactors are being flushed and operated. Using arrays with the Bedrock IDE makes it simple to make very large plants. In this case, the 3-reactor plant is changed into a 100-reactor plant with the addition of a dozen lines of structured text. Notice how the reactors 4 to 100 are implemented in an array. Within the code, the 4th reactor is connected to the 3rd reactor. Then the reactors 5 to 100 are connected to each other in the for loop, and then the 100th reactor is terminated. We can go into the task manager to show how efficiently the Bedrock IDE codes and runs large plants of this size. Notice how the 100 reactors, each containing 4 PIDs, runs in roughly 200 microsecond cycle time. That's how easy it is to design a large plant using the Bedrock IDE and hierarchical programming techniques. Now, if the recipes are different for each reactor, you would need to program those. That could be easily done reading a CSV file developed by your process engineers. The hierarchical design and built-in simulator greatly simplify and encourage the simulation of the control system before it is deployed to the field. The simulation model looks similar to the control model, starting at the plant level with models for the equipment and an overall model for driving the simulation. In this case, the simulation control is implemented in sequential function charts with entry actions in structured text. The signals on the left of the process plant sim are full path names to the outputs of the control code. The signals on the right are full path names to the inputs of the control code. These are the same exact path names that will be used to map the physical I/O modules to the control code. When the code is fully verified, the simulation model folder is removed from the build and the control code is connected to the physical I/O. Notice the process plant sim is run in a different task, which is set at a different asynchronous sampling speed. This is to better simulate the real world where the plant will not necessarily run synchronous to the control code. Pushing further into the reactor simulation model reveals simulation models for the tank, augers, and heater. Again, the signals on the left are control code outputs, and the signals on the right are control code inputs. The actual simulation code is simple and written in structured text. The tank model has 4 lines of code that integrates the difference between the flow rate of the inlet pump and the outlet pump. The auger generates pulses based on the inlet speed. The simulation can be extended to include a full self-test as shown here in the conveyor simulation model. When the run full out not run test is set to false, the system will change from a normal running mode into a self-test mode. In the self-test mode, the system runs all the corner cases of the conveyor and verifies that the system works correctly when it is being loaded but not offloaded, offloaded but not loaded, loaded with the limited stalling, and offloading limited stalling. This self-test becomes a permanent part of the project, so it can be used to verify any modification made to the plant in the future by engineers who are not involved in the original design and might not understand all its subtleties. It continues to be a great tool to assure the program changes will work when they are deployed and will continue to work throughout all the variations of plant operations. As mentioned earlier, Bedrock has developed function blocks to analyze and tune your control loops. These blocks can be placed anywhere in a closed loop to analyze the open loop response. Additional analysis blocks can be added to analyze portions of the control loop. The full loop analysis is performed here with the loop analyzer instance. Normally, the PID output derives the pump motor speed directly, but when analyze loop is true, the body analyzer block is inserted into that path. PID in analyzes the pump, tank, and sub portions of this loop with the pump motor speed input to the pump VFD drive to the sub output. That's the pump, the tank, and the sub block. We can view the loop analysis results in a trace. The loop bandwidth is where the total gain around the loop is 1.0 or 0 dB. This occurs at 5 Hz. The phase margin is the phase at the loop crossover frequency, which is 43 degrees. 43 degrees of phase margin will provide an undamped loop response and will exhibit ringing in the time domain. At 5 Hz, the phase shift through the motor and tank is roughly 116 degrees. That's 180 minus 64, with a gain of minus 43 dB. As mentioned many times in this demo, the power of the Bedrock IDE and OPC-UA provide unprecedented integration between control and HMI. In this case, to connect an ignition reactor template to a Bedrock ignition function block, all we need to do is add a new instance of the reactor data type from the library, give the new instance name of the Bedrock reactor function block instance, and drag the fully functional template into our main screen. So let me demonstrate. We'll start out in the Bedrock IDE here. We'll make a copy of this reactor so we can add a second reactor. And all we have to do is give it the name reactor 2. It's automatically exposed using the attribute to the OPC-UA. So all we do is log into the controller and get it started off and running. Then we go over to the ignition screen. We just create a new instance of the reactor. We give it a name. The name within the ignition doesn't really matter. What really matters here is the name that we give it for the reactor name. And again, going back to review, this is the instance name of the second reactor, R2. So over here we just give it R2. We say OK. And we have a new instance R2 over here. We drag that over to our screen. Size it to the right size. Save and publish that. And go to our publish screen, update that, and here we go. We've got 2 reactors now running independently of each other. So let's just, these all have pop-up menus for their sub-instances. In this case, the reactor. We can go to this one. We can take it out of the program mode and we can stop it. So the motor's now stopped. This motor's now stopped. So after we fill with the inlet liquid, you'll notice these 2 augers run. This one's not running, and so the state machine won't proceed on. This will sit here and do nothing. This is where you'd get a call from your to your service technician in the middle of the night, say something's not working. For some reason my dimethylsiloxane auger is not running, and so he would come into the plant, say something's wrong with my R2 reactor. Let's take a look at it. What could be wrong? Well, we are looks like we're stuck adding DS. For some reason our pulses are not being satisfied. The other 2 ingredients worked fine, but this one seems to be stuck. So let's take a look at why is that stuck. We're telling the auger to run, but let's look more closely at that. So we're telling the auger to run, but the auger isn't running. I wonder why is that happening. Well, we could either push in and look at our the relay ladder logic, figure out what's wrong, or we could just see that, oh, here we've got operator mode is on and we're commanded to stop. So for some reason the operator has commanded this to stop, and we go back and look at our, sure enough, well, so he would come in and open this up. Yep, sure enough, our operator mode was turned off. We'll turn it on, it'll fill with that ingredients, and it will do its agitation now and empty and continue on. So that's how easy it is to instantiate a function block within the Bedrock IDE and instantiate a matching faceplate for that within Ignition. Okay, so that concludes the Bedrock IDE demo. I hope you found it useful. If you'd like the material we talked about in the first slides, please contact your Bedrock channel partner. You can find them listed on the Bedrock website, www.bedrockautomation.com, or feel free to contact me, gary.pratt@bedrockautomation.com, and my number is 408-318-7175. Thank you.